function. In this case, three-dimensional function. You're talking about you want to integrate this function somehow to get this b. So if we want to think about this force and pressure, and this is where I want you to have so this is the purpose of this course. Yeah, I usually mention this many times. It's about deep thinking. So how do you define pressure in general? You have pressure by definition. Now I'm going to use the capital P here. It's just a value of a single value. Yeah? It's a scalar value. Here, this is a function. So it's a small p. It's a function. So this is a single value of pressure is given by a single value of F and area, right? Is that how you define pressure? Agree or not? Yes or no? Okay, Zingong. So usually in my class, I'm going to use this because I'm going to use this triple like equivalent here. It's just define. Yeah, we define P here being this. But look at if you want to have like a relationship between these two. You see the problem? P is a scalar value here. And somehow we're going to make it equal to force, which is a vector, right? Force is a vector. So what do you do? How do we make this? So P is F over A. Later on, this is going to be like a small delta A, but I'm just going to keep it at like before, like this too. So what do you think? How do you make the right hand side? So if you look at this, this is not a correct equation, right? Because the right hand side is a vector, the left hand side is a scalar. How do we turn this into a true statement? Does anyone have an idea? Anyone? Nope. Okay, let me check first because I want to make sure that always when it comes to force and vector, force is a vector thing, and when we deal with vector, we have to deal with direction. When we deal with direction, then we have to sort of like set our reference direction, yeah? Which one is positive direction, which one is negative direction. So yeah, Xin Huang, in this case, area is gonna have a direction. So we're gonna define area as having a vector. And then this is where you see the concept of force, right? It's acting. We always define pressure being acting to um, um, in the direction normal to the surface here, right? It's normal to any to this small area here. So if we define whatever area, and now what I'm going to do is I'm going to define um, a small area. So my small area here would be, it has a normal vector, and I'm just going to call this delta S, as like a small, so S for small. Okay, but you get the idea here. Yeah? The normal vector. So if I define what I want to do now. So this is where I want to make sure that um, I define this correctly. I'm going to define n as being positive um, to okay. This is where I have to relate to the object here. So if it's pointing from the surface towards water, then this is a positive n. Okay, so that's how I define n. So with this, now you can see that I can have a small value of okay. So I'm going to bring force here because eventually F is what we're going to integrate. So F is this P. Remember, and they're both functions, and then I'm going to have the NDS, yeah, that small area, and then oops, sorry, and then it has the normal vector here. And as you can imagine, because when I define n to be pointing outwards, by definition, pressure is acting to, because we are looking at the surface of the body, and the body experience pressure towards it, so it's going to have the opposite direction. Yeah. And this is where, to represent this, you can see how it looks like here in terms. So what I'm going to do is I'm going to, first of all, just draw two different views here. Yeah. First, I'm going to draw, because this is a 3D object, and then it's symmetric along its axis. We can look from the point of view from the, let's say, from the front, or by definition, front here. And then from the side, it looks like a simple rectangle. Okay, this is not a nice drawing. Let me try to draw again, because I just want to, okay, I'm just going to extend this here. Just to make it, to look at same level, which it is. So this is the same object, but just different view. Yeah. Now what you can see is, we can, so how does this the force due to the pressure looks like on this solid object. So because we are saying that the force comes from pressure, so if it's at the same level, you're gonna have, let's say, the same magnitude. So I'm just gonna, and then the deeper you go, the more the magnitude, right? So I'm gonna represent this by a little bit long arrow pointing up there, right? We know that the maximum pressure is at the bottom there. Now you can see, because this is all flat and in the same level, they're all being distributed equally. I'm not going to draw too many lines here because it's gonna mess this, right? And then now, okay, we will look at the water line. This is basically it's basically zero pressure here, just at the exact location of that water line, because that's where we define zero, and then so you have zero pressure here. And you know, okay, in this side, okay, let me just put it this way here. That's also because we are looking at this surface. It's normal to this vertical surface. You're going to have something like this. So you see what I'm trying to show you, right? Because pressure is proportional as you go towards the depth. Sorry, I have um, got this. Now I need to hit this. Okay, all right. So to continue, so it's proportional to the depth. So you can represent it as like a quite proportional arrow going to here, right? So this is your representation. So yeah, what is interesting is on for this um, the round shape or the circular shape, right? You can also imagine how it looks like. So it's going to be hard to to draw this, but okay. I think it's going to. I'm just looking at it. Okay, so if this is the center, so this is where you get like sort of horizontal here because it's perpendicular to this, and then you see that it's going in that way, approaching to this vertical line, and sort of that way, and then it's getting smaller and smaller as you reach the surface. So see, this is how we represent, because this is how we visualize this force vector in XYZ here. And this is also something unusual in a sense, because we don't care about the force within the solid. Yeah, we are just looking at the force at the surface. But of course, there are line of forces everywhere, but we just keep it to the surface, and you can see that is somewhat discontinuity in here, because we don't represent the force inside it. It is it's irrelevant, right? Because pressure is defined by force acting on the surface only. Um, so this is where you can see that the since you are um okay, should I, because you are dealing with the force as a as a distributed load and as a function, and you really want to integrate this, right? Because to get like a total value. Yeah. So if you so total, let's say total force would be um, the integral. Let me, because I have to keep this this negative value correct. Um, so I'm going. So the idea here is to um, integrate over the surface. So we're going to have like a double integral. Yeah, and then let me think for a moment here so that I don't get this confused. Um, so I need to have a different, let's say for now, I'm just going to use like, because we are talking about the surface, I'm going to use d, now it used to have like a, let's see, um, for now we just used here a as a small area in this. So this is some of the force, but now we are going to look at what is inside here. Okay, and this is where we are going to define F. Not just recall our definition of F here. Um, F is F as a vector is negative P as a pressure, and then you have this normal vector and then ds, just like before. By definition of this this whole uh, setup here, the whole concept. So this is where I need to be clear. This is P, but then we have, what is our P? P is that pressure. If it's in liquid, P as a function is just rho GV, right? Rho GZ. And because of the way I set up my my coordinates here, what I'm doing here is this is my 0. So going, so I'm just keeping it like plus, this is a positive Z. And so just want to make sure that I think that's how I define in my book, right? This is basically what is being written in my book for the calculation of this Archimedes principle. I didn't open it yet. Let me find the PDF file. circum-inch. Okay, so we're right here. Somewhere I think I showed you the, where is the coordinate here? Yeah? That's how I define the z, and in this case the z and x. So coming back to my note here, so going downward, it's negative z. And so this is where I think last time, because because by definition, I want to make the value positive as we go deeper in the water. So this is, I put a negative sign here so that as the larger the negative z, you have the larger positive pressure. So this is where I have to be careful. This is pressure and this is rho, which is the, right, rho, right? The density of water. So effectively, this three-dimensional functions is just because it's not invariant of x and y. It's just a function of z. Then, in fact, the derivative of p, which is the gradient, you only have the, so I'm going to put this in vector form, only the p, yeah, the term for the z component. Okay, we're going to use this gradient later on. So what you have here, if I want to, now what I have is the total force. The total force is being defined by this double integral of pressure, then you have n ds, and this, as you can see, it's it can be defined in as a, either as, okay, I'm just gonna put this as a complete statement of this. Just p being rho gz. So I'm going to rho gz. Okay. It looks like this now. So there is a negative sign here, and then rho. Okay, we just going to assume negative rho g is just this rho g is all constant, so negative rho g. So this has z and then ds. I'm just going to keep it this way so that you're going to see and compare when we do it in different way. Okay, so this is the first form of that integral. Yeah, it's in terms of a surface integral. Okay, now this is where we want to find the second form, which is given by this by the variation of the divergence theorem. So I'm just going to write it here. It's a variation. I'm just going to put this as a something that to be paid attention. Variation of diff theorem, which is i.e. gradient theorem. So what does the theorem say? It says that the surface integral of a scalar function in x, y, z here times this normal vector, and then you have over the surface of integration is the volume. Well, now it's a triple integration of the gradient of the pressure dV. So let's look at this, and so that means we can define the total force that we want to find before using this triple integral. So let me just do this triple integral. And so now it's a gradient. So I'm just going to write it directly. So, okay, fine. This is fine. It's just going to write it's the gradient of P dV. Now, what is the gradient just now? It's a negative. I'm just going to. Oh, never mind. Later on, I will just next step. I will just rearrange this. What is a gradient of P rho G? A negative rho G. I'll already take out negative outside. And then you have simply rho G. And then this dV. So what happens now is that so this is the nice thing about the end result of the calculation while keeping the direction and the reference points all consistent. What you have here is so where does this I really need to check out again about this direction. There should be a negative. Okay, never mind. I will just put it down here also too. So let's just take this out first with this negative sign, rho G, and then you have triple integral of 1 times over the volume dV. So what you have here is the so what I'm gonna write down, this is where the buoyancy comes in, and so let me just write first rho G, and then this is V. I'm just going to put it because the whole triple integral of 1 times dV, this is just the volume of, I'm going to put this here D, meaning the volume of the displaced fluid here. Okay, but thing here is, I don't know where I messed up my negative sign. What I want to show you eventually is that the total force also becomes, because of the way we set up the coordinates, the function and so on, it also become a resultant force. And this is what we meant by this particular force, which is the buoyancy, being the resultant force that point upward. As a total, there is a single force as a resultant force here, which should point upwards, which is our B here. But for some reason, I forgot how these negative signs cancel out, because this being positive, it should tell us that it's pointing upward according to our coordinate system here. Okay, so now, in fact, this is the point, the final point for this part one here. Okay. Oh, okay, it happens this way. But okay, before I restart, just want to make sure what I mentioned before. So when I mentioned here, define B in terms of the integral of pressure, this is what we are looking at here. This part here, and also this part here. Basically, this whole part here. Okay, so all right. I'm gonna restart this because of this problem. Quit it and restart. Where's the OneNote? Okay. Okay, I have to share it again, right? Okay. So let me put the box again. Okay, let's just gonna, yeah, okay, fine. And so this is the end of part A here. Okay, so now we go to part 2, part B. The reason why I'm doing this is that now it's a question of, if I rewrite this, it's a question of, so we have, so it so happens that the B is also the buoyancy. I use the same letter here, but this is B for the buoyancy. So I'm just going to write rho G, then this in triple integral. So the point of part B is, so this is basically just 1, and then I have dV. So the point of part B is to identify these limits of integration and how we going to resolve this integration in the most convenient way. Yeah. So this is a question of back to vector calculus, right? And how do we? So it's how do we evaluate the portion of the volume here. Yeah. Um, as you can see, there are, okay, there are more than one way to do this. Yeah. Um, so let me just, I just want to make sure that I follow this. Okay, let me open up my solutions tab. Okay. T2 solution section 7, question 3, and then do I have uh, where is that? Uh, uh, sort of things here too. Okay. All right. So I'm just gonna just as I said, there are more than one ways to do this, but the way that is probably easy but not so easy is to think about um, double integration instead. Yeah? So we are going to, because we are evaluate the volume. So this whole thing is, as I mentioned, it's a volume of displaced fluid here. I can now, because it's a cylinder, let me just look at this again. Because it's being a cylinder, okay, on the one hand, you can use a cylindrical coordinate to set this triple integral. You can do that, but I'm going to use surface integral over the top surface here, the circular surface, and then it's just times the length. So it's going to look like, so it's going to be rho g times L being the length of the cylinder, and then there's a double integral of the area for the area here. So I'm just going to put here dA, because my area, so if I were to sketch this cylinder, it's going to look like this. Okay. And what I'm interested is the partial part of this, right? Because it's somewhere like this, right? So this is where I have a different kind of coordinates. Here, this is simply, I'm using first Cartesian, 2D Cartesian, just for start. So this is my X, and then this is my Y, so that I can give some parameter to this area, right? So this is so the area that I want is the one that I shade here. Okay. And it's how so the idea here is how are we going to integrate this? And so before that, we just define. So we know R. So this is R. And we also know that so R is also going because it's radius here. So this is also R. And the distance from the center to the where we define the water line, we said that it's immersed 3/4 of the diameter. So in other words, it's where is it? So this distance here is half of the radius. So now that we can sort of define the certain points of interest, we need a way to set this integration. Okay, this is where I think by now many of you would see that because we are dealing with circle, it is much easier to convert this into okay, sorry. So this is going to into draw back this circle, which is not a very good drawing. First of all, I'm going to now define the shape here properly. We don't, okay, so this is like it's a center, and I don't want oops, it's removed this whole thing. Okay, I have to redraw this. I thought I can just draw so how is it just now? This is the shape that we want to integrate, right? Okay. So if you have this like a cut circle here, and to integrate, as I said, we can put it in a polar coordinate so that what we have is just if I were to sketch the reference point here, so with a polar coordinate, what we end up is just the row there. We have the row as going from the center and the theta, right? It's going or in sometimes I use this is where I didn't use rho. I use R because rho in this problem I already define as the density. So I use R and theta here. Yeah? So you have R and or maybe just put here R and theta that is like going through this. Remember from your calculus. Now, so now this is a question of resolving how to set up the integration, right? And, as I said, there are many. So we start from decisions, how to resolve this volume. Now we come back to this. We want to resolve by just looking at the area. Now with this area, we have to make a decision of this limit of integral because as you can see, we want to integrate from basically, if conceptually speaking, we want to integrate from, let's say, this location of theta going all the way up to this, right? But of course, if you integrate it that way, you have you're dealing with two two parts of this one area, right? Because let's see, let me um, yeah. Okay. The first part here, which I'm gonna just denote by, let's say, this from here to here. So this is going to be A1. And then we have the second part here, the leftover, which is A2. Um, if you know a more straightforward, um, not maybe not straightforward. Okay, either straightforward or um, evaluation that you can do in a single integration, and let me know. Yeah, this is how I approach this. So A1 is going. So what I have here is um, so my A is now composed of A1 plus A2. So for A1, this is integral in this polar coordinate of so because we're dealing with we don't longer need double here because we're dealing with polar coordinates, we can have basically this is from integration of with polar coordinates. You have to just review this. I'm just here to just jot down um, the form here to find this theta 1 and theta 2. Yeah. So this is how we have to resolve it. I want, because if I were to explain this step by step, I'm probably not going to finish. So I'm just going to cut short. From here, the way I resolve this, because what? Because of the geometry that is being defined by the problem here, theta 1 becomes the way I resolve it. Now it's just a problem of geometry and polar coordinate in polar coordinate. What I have here is so maybe I just put it in here, right? Because I have also A2 there. So from pi 3 and what I have in here, 5 pi, pi over 3 here. That's how I define it. And this is half r square d theta. And you can see that for our case here, eventually, when you simplify, when you evaluate the integration of, you have this theta here, right? Because in this expression, theta is basically 1. Inside here, it's 1. When you integrate, you get like theta. Then you can substitute theta 1 and theta 2. Remember, I'm just explaining in terms of what you do with integration limits. I'm doing this fast, so if you cannot follow, you just have to review how we integrate in polar coordinates. And then, so what do I have in here? Where is the other part of the area? Yeah. And then I have the other part of the area here. It involves also how you um, resolve um, the, let's say you have defined a function because we are integrating in a polar coordinate, so you want to define a function that you're going to integrate in for this, and for that it's not it's not very simple if you don't remember, right? But if you recall how we define a function in polar coordinate, and from there how we resolve the limit. So as you can see here, what I want to do is I want to evaluate this area, yeah, right. So this is where it's not, if you don't remember what you do, um, um, what you do or how you did it in a polar coordinate, and then the transformation between the transformation between the Cartesian coordinates and polar coordinates, this can be confusing. Yeah? And it may also be confusing because I am speeding up this discussion. But this is what I just want to, for our session here. The principle is this, yeah, it's just going between these polar coordinates and uh, scalar, sorry, Cartesian coordinates. Yeah, like in Cartesian coordinates, this line here is, it is just defined by y equals to half r. Yeah. So how do we include this information if you want to set the limit of integration from here to here, and then from here up to y here. So I'm just going to define to you here what I did. I'm just skipping here. If you don't know how to read, you can ask me later. Yeah? So the setup of this A2 would be its integral. Okay. Um, I already use psi1 and psi2 there. Here, maybe I just use psi3 and psi4, just to make it consistent here. So the function that I'm integrating is, so half r over 2 cosecant. So this is where it gets quite messy here. Cosecant theta square and then d theta. Okay, remember all this is just because of the transformation between the Cartesian coordinates and polar coordinates. You can, if you were to do this, you can do this. Yeah? And by resolving this becomes, you just resolve the geometry. This is pi over 6, and this is 5 pi over 6 over 6. All right, so if you do this, so I'm just going to give the answer right away. Yeah. So for A2, what I get is square root of 3 over 4 r square. Yeah. For this evaluation, what I get is where is it? My A1? Oops. Yeah. This, from my own calculation, this is 2 pi over 3 r square. Yeah. So if I were to evaluate to just sum this up, then I get um, um, so okay, I'm just going to skip this because 5 over 6 plus square root of 3 over 16 d square. So this is already, I convert, yeah, from r to d square. Okay, this is the area that I get from my integration. Um, okay, and then plug in the area here, and then you have the length, so you get the volume here. At the end of the day, this is for that reason. If you, okay, I'm switching to my, so where is that practice problem? This is why I put the answer for you here. So that you can compare, because this is not uh, a short integration process. Yeah, so I can, from my side, because this is the problem is defined by myself. So I have to find the solution. And this is not from some other. I don't know if you can find from any other book or online. Yeah? I don't know, but I just define it by my own, and then I solve it by my own, and this is what I got. Yeah? If you if you found it to be different, please let me know. Yeah, one of us can be wrong. So, but I'm quite sure this is already correct. I've been doing this for I don't know 2 or 3 years. I think some other students before this also got this answer. But if you don't, please reach out to me. Yeah. So this is the final answer. Now, before we go to some, if you have any questions, the reason why I'm showing you here is, one of the reason is to show you, if I were to ask this, uh, because I can ask this question in different ways. Yeah, if I were to ask that you set up the integral, then you must find the limits of integration. Yeah, that's obvious. Yeah. But I can also ask you that, okay, they're given this shape. What is the geometry? You can use any method that you want to. What is the volume of the geometry? You can use any method to find the volume. Yeah. So that's my point here. Depends on exactly what I will write in the question. Okay. Just want to make it clear here. So this is the end of this solution step. What is it that you want to ask? And if you have anything to ask about this problem, or in divergence theorem, or buoyancy in general, any question? Uh, is everyone still with me? Okay, Zinghan still with me. Thank you. So no question. Um, do we still have people in here, or I'm talking to only a few? Okay. All right. Okay. So fine. I'm gonna just maybe spend 20 more minutes for this modeling. Yeah. Um, and so 20 minutes for modeling, or maybe 15 minutes, and then 5 minutes to wrap up everything. Okay, so modeling. Okay. Um, I don't know if I have modeling in my slides here. My modeling part is very, very short. Let me see. Yeah, okay. All right. So modeling, as I mentioned, it's only 2 slides. Okay. This is what I want to do. First, so let me get to a new page. Modeling is a big subject in itself, yeah? And for that reason, we have EMT 302, which I also teach. Yeah, that would be in your 3rd year. Um, so what I want to do here is just to give you a very broad overview, and then just focus on one aspect of the modeling kind that you are dealing with here. Yeah? So if I were to think about this like in some kind of idea, so when we have a mathematical model, it can have very diverging types and kinds from here. Many things. Yeah. If you think about this, what you do in physics, for example, F equals to ma. This is one kind of modeling, right? And then so I want to, before we zoom to what we're doing here, I'm just going to take it in a broad way, right? So when you remember, you do, how do I or give you the perspective of this? If you think about prediction, yeah. When you a very simple prediction, yeah, flip coin, yeah, a toss of coin, head or tail, you have this like what we call a probabilistic I don't know how to spell it, probabilistic model, right? And this really have very close relationship with statistical model, yeah? Statistical model. So they are all part of mathematical model. And then from here you can branch into like machine learning, right? The machine learning model, and which is based on, comes from probabilistic model, statistical model, and then with computer algorithm, which is comes from also different kind of model. Yeah, the finite machine, I don't remember what it's called, all this finite space modeling and so on. So it becomes another kind of model in itself. So coming back to what we are doing here. So if think about this, if you are in strength of material, yeah. So if you stretch, let's see here. If you know this setup, right? If I have an elastic material in here, yeah. If I stretch this, if I give some force here, stretch it, then you know how this thing can elongate, right? Because it's being elastic. So subject to this, then remember, right? This is something like a F equals to, what is it? Kx. You can get the, this is Hooke's law, right? Um, if you, so you can know this, what is this, let's say the delta L and so on, right? So this is a part of this modeling too, right? But if you look at this problem, by using this model, you can only describe what is the elongation, right? You cannot really tell what is the displacement of how does this thing displaced? How does this, if this is like think about this, if this is plastic, a plastic material, how does the shape change subject to this force, for example? So you want to do that, you have to determine how this each of these material is being displaced. So if you are looking at this kind of modeling, so you have a solid material subject to whatever different kind of loading here, just to, I don't know, random or arbitrary force that is acting on this shape, it will be deformed. And if you think about um, the smallest part of this, how it's being displaced. So as a whole, there is a distribution. Let's say you're interested in distribution of displacement. So you are talking about if u is your displacement, you want to know how it's being described in this whole coordinates here. So when you are looking at a model that you want to determine like a distribution. It's like how it's being distributed, right? It can be a scalar distribution. So, and also it can have like a vector distribution. So in this kind of modeling, we are interested in this is what we call in as a field. It's more like a field. I'm not going to call it field modeling, because field model in physics has different definition. But in our purpose in mechanical engineering here, I'm just going to call field problem. So modeling of a field problem. This is what you are doing in the class and next in the part with Dr. Sarah. Okay, and this is why we or I showed you the principle in divergence theorem. I don't know if I go back to, I do have the, yeah, um, okay, let me just, oops, copy and paste. Um, so you have this form of equation that you can build, or you can describe certain or many problems in physics. Yeah. So in this case, it so the problem, the case that I was discussing with you, when you have a body that you so this body, it can, maybe you have a temperature as a hot surface here, right? The surface is hot. Let's say T equals to 100 degrees Celsius, and somewhere in at the bottom here, it's cold. Maybe here T is 10 degrees Celsius. And then you have different conditions at other surfaces here. So um, if I want to know, let's say now temperature at I don't know, certain X1, Y1, Z1 here. So how do I do this? How do I solve this? So it comes from these equations. Yeah. So then you have to define in this in more detail, right? And then if you look at this, you have so you have this derivative with time, right? So when you say um, uh, if no time effect, i.e. Steady state, right? Then this becomes zero. So you end up with this terms only, and then alpha here. So, and also because you have zero on the right hand side here, and you can write it in this way: u equal to zero, right? So think about this. Yeah, this very compact equation described the behavior of how the heat is being distributed in this solid. Okay, so when you have this plus the boundary conditions, then you can find the solution of u x y z here, which now can give you the answer to this problem. Okay, so okay, I don't want to restart again because I'm just going to finish this one. So you can see if this is in 3 dimension, you're going to have something like this, right? So if we were to write this in a more lengthy form, this is just like this, right? Y squared plus square u d z squared equals 0, like this. So if this is in 3D, if it's in 2D, you have simply what? partial square u partial x square plus partial square u partial y square equal to 0, right? And if when you, yeah, now it's stuck there. Um, so I have one space left. If it's in 1D, you simply have d square u dx square equal to 0, right? So now there's no longer partial derivative. You have dx square u plus dx square like this equals to 0, right? Of course, when you look at these equations now, you don't expect it u to be 0. Yeah, this is where you come back to that integration and applying boundary condition and then so on, and then you can find what u is. And this is what will be done in Dr. Siti Sarah's part. Okay, so this is very very express way of me teaching you about modeling, yeah. Because I want you to get the continuity of understanding, yeah, from my part here with the divergence theorem and then going into Dr. Sarah's part. So we are basically done with all the topics by myself. All right. Another thing, yeah, before we really end this up, it's not, it's something that you should be aware of when it comes to this this business of outcome based learning here. Let me look at the syllabus, the COPO, and the course outcome and so on. Yeah, this is the thing here that it's like a review, what we're trying to do. This is very tiny for me. So what you have done all this while is just to reach this outcome, yeah. As you can see here, if you look at the first outcome, don't just look at this in terms of mathematical modeling section that I just mentioned in 15 minutes or less just now. What you've been doing all this while with me and then later on with Dr. Sarah is to enforce this. Yeah, the idea that you are able to relate when you come across with some problems in physics. Physics and engineering is just not much different. It's just in terms of the technological aspects of it. But when it comes to the laws, we always come back to the laws of physics. And the laws of physics, then you have to deal with calculus, differential equation, and probability, and so on. Yeah. So just keep this in mind. Yeah, how to connect what you are facing with the equations that you are going to use. Okay. So so I already mentioned to you about this equation, and the more detail will be taught by Dr. Sarah, yeah, for this outcome 2 here. So we dealt with optimization, and then with the idea of these level curves and then derivatives and all those, and but again it comes from calculus. And then I tried to show you, yeah, how this is being used in optimization, yeah, with the simplex method and then on and so on. Okay. Right, in this part here, so I want to again emphasize this. Yeah, this is where because you're doing coding, right, with me and later on with Dr. Sarah, I will include whether in the test or in exam or both um, questions that you have to know the basics of coding. Okay, so with that, I want to stop now. Um, okay, thank you very much. If you have any questions, there's always a Telegram for you to contact me, either directly or with the group in the group chat. So thank you for being here, and thank you also for attending this from week one. I'll see you again. Yeah. The thing about test is we will discuss on Telegram. All right. Bye bye, and I'll see you and have a good weekend. So I'm gonna stop sharing and stop the recording. So I have a few videos here that I want to edit. It will take some time for me to edit these videos before I upload to e-learning. All right, bye bye, and